Happy return. So logarithm functions continuing, and this time transformations. Now, I am going to assume, if you're going to be watching this video, because this is kind of intended for grade 11s, and you have watched or at least understand what the parent function for the logarithm looks like. And if you don't, or if you've forgotten, I'll put up a link up above there to that introduction. Now, the logarithm function, so log of x, now of course it can have any base. So our base, which is, in this case, I kind of designated it as a b right here. So that b can be equal to 2, it can be equal to 3, 4, 5. It can be even a decimal number. It can be a fraction. It doesn't really matter what the base is. Now, as you keep studying, you will notice that the most dominant base that we use is basically base 10. So we write our log function, so log base 10 of x. Now, depending on the base, the log function will look slightly different, but it will have exactly the same characteristics. So no matter what we do, if you're going to take any base and you would plot it, so it would have the same characteristics in terms of its domain, in terms of its range, in terms of its asymptote. Okay, now it will look slightly a little bit different depending on what that base might be, but you will recall that our actual function is going to approach the asymptote of basically x is equal to 0. So that's the asymptote right there. It's going to come up from the bottom right here. It's going to cross through a 1, okay, and then it's going to start to kind of go in this direction and kind of start leveling off, but still going on off to infinity. So this point right here is basically x is equal to 1. So this is my x, this is my y, or my f of x. That's how it will look like. Now, depending on what the base is, okay, so if the base, for instance, is 10, it might be, a little bit, might tail off on us a little bit faster. The base is a little bit smaller, it might not tail off as much, but that characteristic of the log function of any parent function looks like this. Now, because the base of 10 dominates so much for us, we have basically dropped the 10 and all we say is log of x for our function. And you see that even on calculators, you'll see that you'll have a log and then there's actually no base there because it assumes that the base is 10. So what I'm going to provide you in terms of transformation works for any base. It doesn't matter, but I'm not going to be redrawing it for every single base. I will just assume that we're going to take the standard log function and the base is 10, and then you can extrapolate it to any base. But again, remember, the characteristics and the transformations are going to be identical, okay, no matter what that base is. So, again, this is my log function that I have just drawn it. And now I want to talk about transforming, just like I would for any other parent function. You might run into parent functions of f of x is equal to x, which is linear. You might have run into parent functions which is x squared, which is a quadratic, x cubed, which is a cubic, or x to the n, which is any power function that you might have. You can run into the absolute value function, okay, so absolutes of x. You can run into the radical, or the square root, okay, so the square root of x, okay, so that you might remember. And then you can transform all of these. Now it turns out that the transformations basically provide us the same characteristics, so either compressions or stretching in the x or in the y, and then also a translation, okay, in the x or in the y. So in general, our transformations for any function that we run into, by now, I hope that you can remember, and I'm going to kind of rewrite them. So a multiplied by, now my f of x, so here is my f of x, is equal to, so now I'm going to just concentrate on the log, but it's exactly the same for all. So we're going to transform this in this particular way. I'm going to use d again, just as I did for the transformations for the exponential, okay? And you can take a look at that. Maybe I'll put up a link up above there if you wanted to. And then now I'm using d because I don't want to use b, because b, okay, I use for the base, okay, especially for exponentials or for logarithms. So I'll use the d in here in terms of the scaling, and then it's x minus h, and then it's going to be plus a k. So we're transforming our function. So we're either multiplying it by an a like this, and then inside we're going to multiply our input by a d, and then we might shift it by an h, okay, and then we might shift the entire function by a k. So deja vu, again, so please remember, so what do these mean? Well, the a in terms of a transformation, so what this will do for us, it will either stretch it or compress it in the y. So it's going to either stretch it out, okay, or compress it down, okay, in the I, depending on what the a is. Now recall, so if my a is between, okay, so I'm going to assume that it's between 0 and 1. Now it's the absolute value of it. So this would have been actually compressing. So it would have been compressing it down. All right, so that's what I would have had in here. So that compresses it, and it will compress my log function. So it will kind of squish it down. If my absolute value of a is greater than, so if it's greater than 1, then it will actually stretch it. So it's going to kind of stretch it, and you know, if you grabbed it at infinity here and in here, and it would just kind of stretch it out. So you would see that, okay, happening. And that's for your a. Now, if you're going to put, I'm going to add an extra page here. If you're going to be putting in, and your a is now negative, right? So now if the a is less than 0, then what that will do is, so remember, okay, it will just reflect it in the x. So this is a reflection. So reflection in the x-axis. So that's what a does. Now, for our d, so if you recall, if I take now d, I can actually do exactly the same thing, except here, so if you take d, and it is between 0 and 1, so my a is working on the y, right? So it does compressions and stretching in the y. My d does the same thing, but except it does it on the x, okay? So in this direction, or stretches it out in this direction. So if it is between 0 and 1, what it does, okay, it will actually stretch it out, okay? So kind of just stretch it out within, so this is a stretch. So again, kind of that's how you can remember it. So stretching it in the x. All right. Now, if it is greater than 1, okay, then it actually compresses in some way in the x. So we'll compress it more towards this way. This case for our log, because it's greater than 0, okay, we'll just kind of squish it in here. So kind of push it in this way. So that's what would happen there. Now, if the d is, again, less than 0, then this would reflect it. So this is a reflection, but this is a reflection in the y. So it would just flip it over on the other side. Now, all of these are the same for all transformations for all the parent functions you've studied, kind of in grade 11. And there's a few of them that you had. Now, hopefully by this time, because you've seen it over and over, it becomes a little bit easier so that you can apply these to some examples. And I will do some examples shortly, okay, to be able to show you this. Now, the final thing is, okay, so our h, so we know that the h, so within here that we have, so this is just a matter of, okay, so translating it. So it just shifts it over, so translate, and this translates it in the x. So if h is positive, we'll move it in the positive direction. If h is negative, we'll move it in the opposite direction. And then our k basically translates it as well, but it translates it in the y. So it's either going to go up if it's positive or go down, okay, if it's negative. That's what these translations are. So let's take a look. I'll show you an example, and then we'll slowly try to break it down. Okay. Now, before I show you the example, I want to map this out, okay, entirely on decimals, and then I want to play around with it so you get a feel for what happens when you move the A around, the D around, the H, and the K. And then once you do that, and I hope that you do it yourself as well, you know, pop out, let's say, decimals or some graphing tool, and then play with it. So here it is. So I'm going to define my f of x, all right, as equal to log. Again, you can take any base. It doesn't matter. So I can, you know, take it to the base 2. I can take it to the base 3, okay, to the base 4. It doesn't matter, okay? But what I'm going to do is I'm just going to leave it as log, okay, of x, and it automatically assumes that the base is 10. All right, so notice, so if I do that, I'm going to kind of zoom in here so you can see it. Notice the intersection is at x is equal to 1. The asymptote is, again, x is equal to 0, so it doesn't really cross through there. And then it just kind of tails off. Now, it does go on to infinity, but it just does it kind of slowly, right? It just keeps getting bigger and bigger, but it does it in a slow fashion. So let me zoom in here again. So the asymptote, again, is x is equal to 0. The domain is x greater than 0, so it's everything on the right-hand side. The range is actually from negative infinity to positive infinity, so it is all of r, okay, all of the real numbers. And now for my transformations that I'm going to shift this, so what I'm going to do is I'm going to start shifting this. So I'm going to have my a, I'm going to multiply the f, okay, times d, notice x, minus my h, and then I'm going to put plus k, and a, d, h, and k are just variables, okay, so they're just some numbers that I'm going to play around with. And notice here, okay, so it gave me a scale, and I'm going to play around with them between kind of negative 10 and 10. I'm going to first zero off the h and the k because those are the translations that I have. And now I'm going to just one by one play first with the a, just so that you can see that it will be stretching out, so stretching out, okay, or compressing it in the y direction. So first let's keep it positive, all right? So if I do that, okay, and I start playing around with it, if I make it bigger than 1, so notice it, what does it do? Okay, it pulls them apart, okay, so it just kind of stretches it out, okay, in the y direction. So that's what you see here. And now if I make it bigger and bigger, just keep stretching it further and further. So in this case, stretches it this way, stretches it that way, kind of tries to pull it apart, okay, across that x-axis, okay, so it tries to stretch those out. Okay, so that's what happens there. Now, if I keep the a between, so here, actually let me try. So I'm going to put the between 0 and 1. So if I play around and between 0 and 1, it should kind of compress it in, okay? So it should compress it in, almost like squashing it. So here for my a, so notice it's going to start squashing it. So if it's from 1, this is the original, right? F of x, that's my parent function. And as I make it smaller and get closer to 0, okay, it starts squashing it. Okay, so it starts squashing it. So where this is your x-axis, it will compress it in this direction and compress it in this direction. So it's going to kind of skew it, guys, and you can see that in the black there. Okay, so right there, as it skews it down, it gets closer and closer, almost to like a flat line, right? Just it tries to flat line it. That's what your A does. So that's the stretching and compressing again in the Y. Now, let's go back to the D. So now what will happen to the D? So if I take D, let's say between 1 and 10, so in this case, so what will happen is this is going to work in the x direction, right? So we want to be able to see that this is kind of gets compressed or kind of gets shifted over. So here, let's take a look. So notice that what happens in here as I make this bigger and bigger and bigger, it basically what it does, it takes the original, okay, and it squashes it in this direction. So notice that let's say if I had the point 1, 0, this is going to get pushed over all the way, okay, to this point, which is 0.120. So it just squashes it over. And any other point will get squashed over in that direction. So it's almost like it's getting compressed in here, okay, and it kind of looks like it's getting stretched in the y. Now, if my d was between 0 and 1, then what will happen is, so if I would do this, okay, between 0 and 1, and if I start making it smaller, okay, so let me grab it and make it smaller. So it looks like it's getting shifted, okay, kind of down, but what's happening is you are actually trying to, okay, so this is now in the x direction. So in this case, okay, so what it's going to try to do now is stretch it out, right? So between when it's greater than 1, then it compresses it in, so it pushed it all back in this direction. Now it kind of compresses it, okay, stretches it out as d is between 0 and 1, so it pulls it out in this direction, okay, so it stretches it out in this direction. So for example, the point 1, 0 is going to get pushed out more further out, okay, it's going to get stretched out all the way there, okay, so it constantly gets pulled apart like this. So that's what your d will do. Now, if I go back in here, okay, I'm going to put this also at 1. Now, what would have happened, because we want to see the reflections, if a turned out to be negative, what did we want to be able to see? We want to be able to see that it actually flips it. So there's a reflection in the x. And notice that's exactly what happened. So it just flipped it over. And now if you did the same thing, so here, if I do that with d, that flips it over in the y. Okay, so that's something that we've seen. Now the h and the k, so this one is a lot nicer because all it is just translations. So if the h, okay, so notice it's going to get pulled so it's going to move it in this direction. But when it pulls it in this direction, notice the asymptote moves with it, right? So if you're going to shift it over, it's shifted over by 0.8, which means that now your asymptote is at x is equal to 0.8. It was at 0, now it shifts over because it's a translation, right, in the x. So it's going to keep moving it in this direction, okay, or it's going to be moving in the opposite direction. So that asymptote changes. Now, if you were going to, let me zero this off, bring it back, the k is going to move it up or down. So this is going to move it up or down, but it doesn't change your asymptote for us because it just moves it up or down. It doesn't do anything in the sideways direction. And that's what I would encourage you to do as a student. You can take any function, for that matter, and do that with it. Okay, so doesn't have to be log of x. It could have been anything. It could have been 2 to the x or 10 to the x. Okay, it could have been your x squared, and you could have done exactly the same thing, and you would have noticed these compressions, stretches, okay, and then translations. So I'm going to go back here. I'll zero everything off. Okay, let's put it in this way, and then let's take a look at a couple of examples. So here's an example where first we're going to try to answer these without actually plotting it on a graphing tool. We want to see if we can understand what is happening. And it's asking us for the domain, it's asking us for the range, it's asking us for the asymptote, and it's asking us to sketch it. So we're going to try to do that. All right. And I'm going to do it one by one. So the first thing that I like to do is I actually like to first work, okay, with the compressions and stretching, okay, in the y. So I'm going to work with this a right here. And then I'm going to see if there's a d. Now in this case, doesn't look like there's a d. Okay, so let's take a look. So if I look at this, what I have is, if I map it over to, a f of, let's say, d x minus h plus my k, so I want to know what all of these are. So my a, it looks like my a was -2. My d right here, so notice it's x minus 1, so d is actually 1. So there's not going to be anything happening in the x, okay? My h right here is actually 1 as well, so it's going to get shifted to the right. And then my k, it looks like it's a 5, so it's going to be moved up. So let's take a look and see what happens, and if I can just sketch it and then talk about the domain, range, and the asymptote. So let's assume that this is my parent function, my log x, all right? That's what I have. And now, all right, so first of all, my a, so right here, is 2. So what will happen in here is that, okay, so for my a, so what it's going to do is, okay, because it's greater than 1, it's going to stretch it in this direction. So I know that it's kind of going to look like this. Now, I'm kind of guessing it in here, okay, but it's going to look something like that. Let's see if it, oh, it does it for me pretty good. So it's going to be something like that. Now, within here, so this, will tend, so it's stretching it in the y, but this still tends to, basically, to 0, all right? That is just if I plotted 2 times log of x. That's what this would have been, okay? So that's the first thing. Now, my d is equal to 1. I'm going to do the reflection, okay, shortly. Now, my d, okay, is 1. So there's nothing to do with this. So I don't have to compress it or stretch it in the x in any way. I will have to, okay, so now that I have done those two things, so I always do my a and my d. Now I'm going to try to do the reflection. So the reflection is supposed to be in the x-axis, okay? So, how will this exactly, look like? So I'm going to change the color again here. And so it's going to look like, if I reflect it back, okay? So this is kind of going to look like this. I don't know, I'm trying here. Let's see if it works, okay? So it's going to kind of start looking like that. That's the reflection, okay? So this one now is -2 log of x, okay? So now it's looking like this. Now what I have to do is I'm going to translate it, so 1 to the right and 5 up, okay? So 1 to the right, so that means, okay, so that my new asymptote, okay, if this was 1, okay, so if this was, I'm going to draw it right through here, okay, and then shift it over. So if this is 1, x is equal to 1, so that means that my function, so this one right here, it's going to get shifted, okay, over in this direction, like so. Okay, so let me remove these. So that's what's going to happen with that. So that's my function. So it got shifted by 1. So my new asymptote is basically x is equal to 1. And now it's going to get shifted 5 up. Okay, so it's going to get shifted. So this is going to go plus 5 up. So all of these, so it's going to get moved up in this direction. So what happens is if I take this, okay, I can try to shift it, okay, and it's going to look something like that. Okay, it just gets shifted back up. So this is a sketch of what I have. Again, the asymptote still stays the same. Okay, now my domain, notice that my domain for this is going to be x greater than 1, right? Because I've shifted it over. So my domain is x is greater than 1, okay? And then my range is still going to be, okay, positive to negative infinity. So it's going to go like this. Now it looks kind of deceiving right here because it looks like it flattens out. It actually doesn't flatten out. It just slowly keeps getting bigger and bigger and bigger and bigger, just very, very slow. So let's see it, okay? If I do this, so we're going to input these values, -2, 1, 1, and 5, and let's see if we're going to be able to see something like this. All right, so first let's put here a is equal to 2, so I'm going to do that. So notice the stretch, so that's kind of how it looked like in the beginning. There was no d, right? So d was just equal to 1. So now next what we did was we made it negative, so it should flip it, and it did, right? So it nicely flips it over. Now we want h, so basically pushes it, okay, to the right. So notice now your asymptote, okay, basically is based 1, so it gets closer and closer to 1. And then finally my k was 5, so it's going to move it up. And there you have it, it moved it up in this direction. Okay, so I was actually way off, okay, on that, because when it moved it up, now it's eventually, so notice it keeps getting bigger and bigger in the direction, but it does it very, very slow. So there we have it. Okay, so it kind of looks like that. So we were dead on, except, okay, you know, when I moved it up and noticed that it crossed that x, but that actually happens very, very far away. And you can check it, you know, for yourself if you wanted to, because that value is at y is equal to 0. Okay, so that's kind of how you would be able to sketch these, kind of going back and forth and then trying to see, you know, how far you can push it. Here's another example. So within here, okay, if we wanted to sketch this one, okay, so we can try it to see if we can do it. So I'm going to talk about it and then we'll plot it up. So I'm going to kind of rewrite it. So I have 3, notice log. I have to put it always in the form. Okay, so -2, I'm going to factor out that -2 is going to be x minus 2 minus 1. So here is my a, here's my d, this is my h, and this is my k. Okay, so now let's talk about these, okay, as we scale through, and then we can talk about the asymptote as well. All right, so first of all, okay, so this would have been, so it's 3, so it's still a stretch in the y. Okay, so it still would have been pulling it apart in the y. So that's the first thing that would have happened. Okay, so that's a stretch, okay, in y. So it pulls it this way and pulls it kind of that way. All right, so that's one thing that would have happened. Now here's my d. So my d is 2. So now what did that mean? So remember that if your d, so the absolute value of d, is greater than 1, then it actually compresses it, right? So it kind of squishes it back into this direction. So for that, so this was for A, this is for D. Okay, so D will compress. Okay, so it's going to push it in this direction towards the 0. It's going to start to squish it in there. So that's what we will see. Now we will also see a reflection. All right, so for that D, we're going to be seeing a reflection kind of going back into this direction. So that's interesting. So what's going to happen is, so if you have your graph, so if it's like this, okay, and you know, it kind of looks like that after your A and D, but because of the negative, it's going to swap in this direction. Now, that does not change your asymptote yet, okay, because we haven't moved it. But what it does do is notice that it changes your domain, right? Because now it's x, which is everything, which is less than 0, at least so far. So now what will happen? Well, now we're going to shift it by 2. So it's going to get shifted in this direction by 2. So our asymptote right here, so it's going to be 2 right here, it was 0. So our asymptote is going to change. So now it's going to look kind of like this. I'm kind of exaggerating this, well, maybe too much, but And that's okay. So it's gonna look something like that. It's gonna get shifted in this direction. So now my domain is x less than 2, right? My range is still all of my real numbers. And now finally, so this is going to move it up. So this is going to shift up by 1. It's going to get moved up in this direction. So we want to be able to see something kind of like that, right? So let's see it. Okay. Now, domain again is x less than 2. That's what we want to see. The range is basically all of R, so it's all the real numbers. The asymptote is x is equal to 2. And the sketch should look like our final one, which is kind of something like this. Now, of course, I'm going to be a little bit off here in terms of my scaling. Okay, so let's take a look. I'm going to try to do that. Go back in here and let's change it. Okay, so first off, so this was 3. Okay, I'm going to change these back to 0. So there you have it. Okay, so that's that. Now I've stretched it out so far that you can't really see it. Okay, but here you go. So that's the stretch. My D was -2. So we want to be able to see a reflection. Okay, and then so first maybe let me put 2. Okay, so that it doesn't change much. It doesn't seem like it. But notice that's 1, that's 2. Okay, so we've seen a little bit of a compression, okay, in this direction. And then finally, so this is negative. Okay, there we have it. Okay, so we see a reflection. Now my H was just 1, or was it 2? 2, I think it was 2, because I said the asymptote was 2. Yep, so that was 2. So that's what we have there. Okay, so it shifted it over. And then finally my K was 1. There you go. And that's kind of how we graphed it, right? So that's how we approximated it. So all these translations, okay, reflections, compressions and so on, so transformations in general, basically are the same as you've always done them. Now, I hope that you found this useful. I do encourage you to try it, especially on decimals, play around to get a real feel for it. And if you like, you can even change the base. It doesn't have to be base 10. It can be something else. But just base 10 is so dominant because decimals, we use powers of 10, right? When we represent our numbers, so that's why the log typically assumes that the base is 10. Okay, thanks for watching, everybody. Okay, we'll see you in a future video. Okay, cheers, bye.